Welcome back. I hope everyone has had a chance to tackle part 1 of assignment 4. If you haven't, you really should ASAP. This is the third and final lecture of the assembly language part of the course, where we really dig in and see what we've been missing to be able to translate typical programs from a high-level language like C into assembly language. In particular, our programs thus far have been artificial. We've been using only the BSS and data sections for our program's data, and we haven't seen how our main function would interact with other functions. So this lecture will be talking about the challenges of function calls and the approach ARM takes to support these fundamental programming primitives. Thinking about function calls at a high level, here are a set of problems we need to solve. Calling and returning a function, passing arguments to a function, storing local variables inside of a function, and returning a value from the function. Beyond just solving each individually, though, all of these have to work within a single set of assumptions and conventions. So to explore function calls, let's start with just a straightforward function that, despite being straightforward, has some nice properties for pushing and prodding and stressing our handling of function calls in ARM. absadd takes two longs and returns the sum of their absolute values using the C standard library function labs. It's not concise, it's not super idiomatic, it's just plain simple step by step. We declare 3 local variables, we pass in 2 parameters into that library function, storing the result of each of the 2 into local variables. And then we add the partial results into the third, and we return that value. Let's consider the problems one at a time, starting with calling a function and returning from it. So to start in on function calls, the first thing we need to do is figure out how to actually stop running at one location in the text section and go somewhere else to start running there. Then, just as importantly, at the end of that function, we need to get back to the place where we made the call once the function is complete. Otherwise, we'd call our first function and never get back into our own program. So how do we do this? Take a few seconds and think about what instructions we'd need to accomplish this. Hold that idea in your mind and see how it holds up as we move on. What do we remember from last lecture about control flow? We can use the B instruction to do an unconditional branch to a label. We saw within main that our functions are indicated by labels. The labels are just addresses within the text section that we've given a name to. And so calling is straightforward. We have B to G, branch unconditionally to G. And really, by this exact same structure, just in the opposite direction, we can go back. From G, we can say branch to F's return point. That looks great on this slide, but as you might expect, since the slide is titled An Attempted Solution after all, there's a problem. Take a few moments, pause the video here, and see if you can figure out what the problem is going to be. This looked great on the last slide, but really, why do we define functions? Typically, so we can use that subroutine over and over, potentially in different contexts. Like this. Now we don't have a clear answer for where we should branch back from G, because it's called from multiple places. We need some additional context as part of the function call itself. How is information held in the ARM programs we've seen thus far? In registers. So we could fix this with some additional context in a register. Before using B to perform a function call, put the address immediately after the B instruction into some register, Then at the end of G, branch back to the location in that register. But nevertheless, this is the basic approach that ARM takes. It just gives us some niceties to remove some of the ugliness from the previous slide. We said the three problems were, we need to add an ADR instruction. No longer. The BL instruction automatically puts the return point into X30. We still needed an explicit label after every function call. Nope, not anymore. The BL instruction automatically puts the next instruction after itself as that return point. And we need a convention for what register to use, because the caller and callee both have to know about it. There's no way out of this one. But X30's role is defined in hardware, so that's not just some ticky-tack convention, it is actually defined in the architecture. So with BL, ARM allows us to do a function call with appropriate context in a single instruction. But alas, the title is still only a partial solution. So again, take a few minutes, pause the video, see if you can reason about why this still isn't sufficient for real programs. As I always say, write down your vote, as it were, write down your reasoning, see if you can figure out what is the bug or what is the problem going to be. When you have a hypothesis, feel free to move on. So here's a more complicated example. F calls G, then G calls H. F calls G, so the address in F that's immediately after the BL is put into X30. That's location 1 in the slide. Now when G calls H, the address in G is put into X30. That is location 2 in the slide. We finish off with H, we return back to the contents of X30, location 2. That's all good. We finish off with G, and what's in X30? It's still location 2. What happened to the address of location 1 in F? G doesn't know where to return to because its return address was overwritten when it made a function call. So we need a way to store a function's context beyond just the registers. We need this to be able to save an older value from the context while we go and do later things. Then once we come back from those later things, restore that saved value. What data structure is this? Well, what I just described is LIFO, so we're talking about a stack. And so in the terms of our C programming, what we've learned so far, we need a stack frame. In C programs, we saw stack frames that represented functions that had been called but had not yet returned. This is the exact spot where we can stash the initial value of X30 so that a function can make more function calls. Put another way, all of those stack frames you've been drawing in class, it was a lie. To be fair, not fully a lie, but it was only a subset of what's stored there. Here's what that looks like in principle. In each function, we save X30's value to the stack frame, we go about our business, and at the very end, when we're ready to return, we restore the value into X30 from the stack. Now for the particulars. We're going to use the register SP, a 64-bit register which we saw in the first assembly language lecture. That was one of our special purpose registers. It's used to point to the top of the stack. What this means is that at the beginning of the active stack frame, any new function will have its stack frame pushed on top of this point. To designate space for a function stack frame, we move SP. We think of this as putting it on top of the stack, and since we draw memory from up is low and down is high in terms of numbers, that means that to get a lower memory address, we need to subtract from SP. Note that the ARM requirement is that SP must be aligned to 16, must be a multiple of 16. So even if we have nothing else on the stack except X30, an address, thus 8 bytes, we're still going to have to allocate 16 bytes to do so. Do watch out, because this is a tricky thing you can often overlook when you start writing your programs, and the error message isn't helpful at all. Just allocating the space would be worthless if we couldn't use the space. We can load from the location that SP points to and store to the location it points to. Also, you remember the fancy register offset and scaled register offset addressing modes from last lecture? We can also use these, so we can load from a location it points to or an offset relative to it, and store to the location that SP points to or an offset relative to it. We'll see some of those later. When we're done with the function, we have to restore x30's value. When we do so, now we're ready to give up the space on the stack. Think of this as popping the stack frame off the stack. And how we do that is simply by adding back SP's size. So we move SP back down to a higher memory address. So you've seen a function prologue and epilogue, and it was basically just as mysterious as public static void main string brackets args was in 126. But now the fog begins to lift. In the prologue, we're making room for our stack, then saving into that space the value from a register that gives us the address to return back to at the end of our function. And in the epilogue, we're recovering that address to return back to, since if we made any function calls, it will have changed, putting it back into the register where it goes, and then tearing down the stack frame. So at this point, we can translate a little bit of our running example into assembly language. abzad has a prologue. It has 2 BL instructions to make function calls. It will restore x30, the address that abzad has to return back to. It will tear down its own stack, and it will use the ret instruction, which will simply jump to the location that is in x30. There's a lot more to go, though. Take heart. This was the most complicated problem to solve, and also the most critical building block for solving the other problems below. Now we can make function calls, but how do we get data into the function? Up until now, all the data we've seen was just stored somewhere in a global variable. That certainly won't do going forward. Just like with the return addresses, arguments are something that's handed to the callee by the caller, and the caller has to save it somewhere. Sorry, the callee has to save it somewhere if it's going to make its own function calls using the same paradigm. That place for x30 was on the stack because we couldn't know how many function calls would happen. The exact same argument, no pun intended, applies for function arguments. Perhaps you recall from our initial ARM handout, it noted that the first 8 arguments to a function are passed in registers x0 through x7. So these are just like x30. There's just more of them. Note that it's possible to pass even more arguments. You'll just have to reference them on the stack frame directly, and we won't deal with that in 217. Similarly, these registers are only 64 bits, but it is possible to have data structures that are bigger than that, for instance, some structs. Again, the answer is that they're passed in via the stack, but again, we won't deal with that in this course. So just as with x30, if we want to call our own nested functions, or in this case, if we want to use x0 through x7 while retaining their argument value, we'll need to store their values onto the stack for safekeeping. Once on the stack, we can reference these variables as offsets from SP, just like we implicitly did with the stored value of x30 when we had it at offset 0. We just don't normally write that offset 0. In our running example, we'll definitely save to the stack, because other things we do might corrupt the values of x0 and x1. In particular, when we make function calls to labs, we'll have to put those arguments in the same set of registers our arguments came in. So let's look at the assembly. We have 2 more str instructions to save register values into stack memory. Note the register offset addressing and how it places them at 8 and 16 bytes added to SP, so down the current stack frame, below the stashed X30. When we're ready to call labs, we have to get into X0 the value A, because X0 is used as labs' first argument. It's already there, so we could just go straight to the BL, but in the spirit of establishing an idiom, and because, frankly, those circles of ellipses might elide something that overwrites X0, let's load it. And before the second call to labs, we certainly have to get B into X0. X0, as we last knew it, had A, not B in it, and again those ellipses. So now we're all set. We've passed in the arguments into registers, and where we found those registers wouldn't retain the values, we saved them somewhere that wouldn't get corrupted, in this case the stack. And that actually matches how we've been perceiving parameters in C as being kind of like local variables, just on the stack. Note that we've changed the size of our stack allocation to be 32, since we need to store 2 long parameters and a return address, a total of 24 bytes, so 16 wasn't sufficient. But recall that we have to maintain being a multiple of 16. So 32 it is. Now let's clean up something super ugly and artificial we've been doing this whole time, using nothing but global variables. In C, we've said that local variables are stored on the stack in their function stack frame. What about ARM? Well, there are an arbitrary number of local variables, and we need to keep their context forever until the function returns, even when there are other functions being called in the meantime. It's the same set of conditions, and indeed the same solution. We should use the stack. With this, our running example is almost complete. The core of our own code, the sum gets abs A plus abs B C line, breaks down into at most 4 assembly instructions. Load the local variable abs A from the stack into a register, load the local variable abs B from the stack into a register, do the addition, and then store the result into the stack at the location where at the offset where we've set to be sum's location. Note that we do now need to store 3 local long variables, 2 long parameters, and a return address on the stack, so our prologue and epilogue have expanded to 48 bytes of stack memory. We're almost there. The only elided out code in this last version was how to deal with the return values from functions, and consequently how we'll return our own. We saw this in the first lecture, noting that by convention the register X0, or its lower half W0, in the case of a 4-byte entity, is used to store the return value upon exiting the function, and returning control back to its caller. So that's the answer, but let's take a deeper look. In principle, we could do the same thing as we did with the return location. Have a register that's passed in that indicates the location in memory, this time on the caller's stack, where the callee should place the return value. And for more complicated data types, this is actually what happens. And indeed, more generally, we can have output parameters from functions in a similar manner that we can in C. But typically, since our C functions return one thing, and in the scope of this course, for assembly language that will always be a character, a short, an int, a long, or an address, we can just use a register, X0 by ARM convention, and store the return value there. So here's our running example, finally fully fleshed out. After each BL to labs, we're going to store away X0, the return value, into the appropriate local variable. And when we're set up to return from absat ourselves, we'll reload sum into x0 to be our return value. I've done each of these steps relatively quickly, but I encourage you to pause the video here and walk through the instructions one by one, convincing yourself that you understand what it's doing and why. Formulate any questions you'll want to ask in my Piazza post, or so long as the video is paused, go ahead and post them now, or back up in the video and go back to where I talked about where each of these lines came from to make sure you have a solid understanding. Okay, so that's a working program. It's perfect, right? Of course not. For starters, let's just check out the very last thing we did. You might note that x0 has the value we just stored into sum, so that seems like a waste. Funny that I think of that. The last bit in our talk today is optimization. That is, improving working programs to be good programs. This consists of time and space optimization, but also program clarity. We'll start with the former because it'll make even more problems to clean up with the latter. Recall in the first assembly language lecture, I noted that we'll be talking about the storage hierarchy soon. But all that we need to know now is that registers are fast but tiny, and memory is huge and slow. Well, all that nice stuff I kept talking about with how do we solve this problem? Use the stack. How do we solve this problem? Use the stack. The stack is memory, and thus slow. So it would behoove us to use the registers as much as possible. For example, dedicating a register to a variable and just keeping it there the entire time. The problem becomes, though, that there are only about 30 registers, and some of them have special uses like parameters, and we might have lots of functions. There's not enough to go around. So this is a promising approach for optimization, but we're going to need to think more carefully than just put everything in the registers and voila, it works. In the face of scarcity of registers, we want to make sure that every function has something they can make use of with minimal slowdown of having to go to memory. The way we're going to do this is to have some registers that are guaranteed that a function you call won't corrupt it, and others where we don't have that guarantee. In that same original handout from the first ARM precept, each register was noted as either callee saved or caller saved. Let's explore that. Callee saved registers have a sort of guarantee, kind of like what we saw with pointers to constants, in that the caller can expect that these values won't change. So if I have the result of my secret formula that I've done years of computation to produce, and I store it in x19, I can be sure that if I call printf, printf won't corrupt my precious result. That's a win for me. I don't have to use memory on the stack to store away my result before calling printf. But on the other hand, that means for printf, that if it wants to use x19, it needs to save away my precious result onto its stack frame so that it can restore it to before it returns to me. That would make it look to me that it hasn't touched the register. Furthermore, since I am someone else's callee, before I put my precious result into x19, I need to store away my caller's x19 into the stack for safekeeping. So using callee saved registers is always a trade-off. You'll have to save and restore once yourself, but then you get to use your callee saved register as much as you want in between without worrying about what other functions that you call do. Furthermore, if they don't use it, they don't have to save and restore it. So this is typically a win. On ARM, registers 19 through 29 are callee saved. The opposite side is caller saved, which are x0 through x18. If I'm calling a function, I have no guarantees that the function won't corrupt my values in these registers. In fact, looking at x0 as one of them, I can be almost sure that they will corrupt that one since that's the return value. This is a win for the function I'm calling because they can use those registers with impunity. But of course, for me, it means that if I was using them for something important, I have to save those values to memory. In a typical approach, we use caller save registers for as much as we can. But when we know that we're going to have a variable that must persist across several function calls, it may be worthwhile to put it into a callee saved register. Let's see how this works for a running example. In our initial version, abs_add takes in parameters and stores them on the stack, then loads them back into registers before each of the calls to BL. If we think we'll be using our parameters repeatedly, we could store them into a callee saved register instead of onto the stack. But of course this means we'll have to put the initial value of those registers onto the stack so we can restore them before we return. For now, let's assume this is the case. We'll use all callee saved registers. If we end up not making good enough use of them, we'll reoptimize. We can do a similar thing for local variables. In our initial version, abs_add allocates all 3 local variables on the stack. It stores and loads from the stack several times in the program, storing after each BL, loading to compute the sum, storing after the sum is computed. We can again choose instead to use callee saved registers for this, at the penalty of having to save and restore each of their original values once. Again, let's forge ahead and assume we'll do this for all 3 of our local variables. This is what we come up with. 5 callee saved registers are stored on the stack so they can be restored later. And those 5 registers that we just saved are used for the 2 parameters and the 3 local variables. Every time after that we reference the parameters or the local variables, we're going to be using the registers x19 through x23 instead of interacting with the stack. We don't have to protect anything before calling labs because labs can't corrupt any of our callee saved registers. They're callee saved after all. We use a move rather than a store to save the return value from each call to labs, again, doing a register operation instead of a memory operation. And we don't have to interact with memory to set up our addition, nor to set up our return value. In the end, though, we do have to restore each of the callee saved registers, including x30 as always. At this point, though, we can look and see whether all that was necessary. Some are easy. We definitely had to save away x30, just like always, because we make our own function calls. A comes in x0 and is immediately used as the first parameter to labs. The first parameter goes in x0, and then it's never used again, so there's no need to have it be persistent at all, and thus no need to use a callee saved register for it. After computing abs_b, we don't really need to store it back into the local variable that was designated. Instead, we can just use x0, the return register from our method, into our addition operation. Furthermore, with that addition, instead of storing the sum into the local variable designated for it, we can continue just to use x0 as the destination because that's where it ends up anyway as the return value. So some calls are easy. Others, though, take some analysis. B comes in x1 and it has to survive the first call to labs, so we better save it. Saving it in a callee saved register requires 1 memory write to save the old value of x19, 1 register write to save B into x19, 1 register read to pull it back out of x19 into x0, and 1 memory read to restore the original value of x19. Not too bad. But had we stored it on the stack, it actually would have been even easier. It would have been 1 memory write to store it, 1 memory read to load it, and no cleanup. So in this case, even though it had to survive a function call, maybe it would have been better not to have bothered with a callee saved register here at all. But in the general sense, hard to say. My best advice here is try it out, see what helps, see what doesn't. Keep tons of working versions for comparisons. Note that parts 2E and 2F, the latter being the challenge part, of assignment 4 ask students to hand optimize their assembly code from part 2D. The goal of 2E is exactly this, to use registers rather than stacked memory to store your variables. So you'll want to study these last couple of versions of abs_add carefully when you start out with 2E. In general, we're going to try and not do hybrid patterns. We're going to try and do either an unoptimized pattern or an optimized pattern. Our unoptimized just means we're keeping all of the parameters and local variables in memory. Our optimized says keep them all in registers. As we saw, there are some cases where we can trend towards a hybrid pattern because it's just silly not to. But hybrids are very error-prone for humans, even if they may eventually prove fruitful with diligence and effort. Note that the GCC compiler, as is the premise of assignment 4, has a -O option that can try to do optimization of its own. The last part of today's lecture deals with how to maintain readable code within the mess of stack pointer register offsets, registers being dedicated to variables, etc. Look back at our second to last version here, the one before optimization. It's tricky to read as is. And if we take out those thorough comments, even with the C code comments still there, it takes some real stretching to figure out what's going on. We don't encourage inscrutable code in C, so why would we in assembly? Let's see how we can fix this up. Just as in C, where we had enums to give readable, semantically meaningful names to integers, in ARM we have the EQU directive. So for example, if we're developing and we aren't sure how big a stack size we'll need, or just to be clear in the prologue and epilogue of what the heck we're doing, we can put stack size as a constant and use it in both places. Similarly, just as in C, we use good variable names, and when we're dedicating a register here, we should similarly use that good variable name. We can do so with the .rec directive. Note the infix syntax, which is different from most of the directives we've seen. This allows it to give the sensible name that presumably we had in C as the variable to the register that we're dedicating to it. On this slide, we see there's a little bit of overhead in terms of text up there at the top, setting up these symbolic constants. But at the bottom, we start to see the payoff, and it'll continue on the next slide. Here on this next slide, we have the sum operation, the add of into sum of abs A, abs B. It's so readable that even if it weren't standard to use the C comments, we probably wouldn't have commented at all. This makes it much, much easier to read at the expense of some overhead of defining these constants. At the bottom here, you see that we still have a whole bunch of lines that have magic numbers of stack offsets. And in this code, we've chosen to just comment each line to indicate what's going on. We could have made a different choice. We can go even one step farther using variable names or other semantically meaningful modifiers for offsets on the stack. Here it's not a huge deal because we only have to save and restore once. We could get away with just a comment. But you can imagine that when you're storing variables on the stack and storing and loading it all the time, as you're going to be asked to do when you have a faithful translation rather than an optimized one, you'll want to have that variable name as the offset for sure. Again, in this case, perhaps overkill, but for stack resonant parameters and local variables, it's definitely a must. So this ends our primary lecture coverage of ARM assembly language. We'll see a little bit more in passing later on when we talk about machine language leading into assignment 5. With this material, you now have everything you need to go on to the assembly language programming of the big int larger and big int add functions as part 2D of assignment 4, and to optimize them to use callee save registers instead of stack memory in part 2E. You're also as ready as you're ever going to be to attack part 2F, the challenge portion, in which we encourage you to go as wild as you want and try optimize to beat the compiler and more. If the material in this lecture still seems mind-blowing, nitty-gritty, or frankly even if it doesn't, make sure to catch Precept this week, where the content is completely focused on assignment 4. In Wednesday's lecture, we'll cover some further motivation on assignment 4 and the technical details of doing part 2C, in which you run a standard performance analysis profiling suite. But don't wait until then to keep working on A4. Now is the time to dig in, get your hands dirty, learn to love GDB with the first precept this week, and of course have fun.